Hello everyone. So now we are going to continue the class, that is magnetic effects of current. So next topic is Lorentz force. Magnetic Lorentz force. Complete sentence is magnetic Lorentz force. Why? Because Lorentz force is also there in electrostatics. So that is why specifically we say magnetic Lorentz force. Okay. So combined Lorentz force is also there. I mean both electric and magnetic field Lorentz force. So that is why like here let's Lorentz force it is, and we will discuss that one by one. So what is a Lorentz force? When a charged particle enters to a magnetic field, okay, a uniform magnetic field, so there will be a force acting on that charge. So in the first class, in the first session, I have told you why there is a force between the moving charge and the magnetic field. So that I told you. Why? Because we all know that, look at this, if a charge is moving, this is Q which is moving, then there will be a magnetic field around it. It will produce a magnetic field that we have learned already. So that is why there will be a magnetic field over here, and this magnetic field and the existing magnetic field, both magnetic field will interact each other. That is the reason of this one. I mean the force between them. Alright, so I think you have got it. So there are two magnetic fields, they interact each other. That is why the force between two magnetic fields. Alright, so next is how much is that value? So look at this. In physics, everything we discuss, we have to measure it. So Lorentz, the scientist Lorentz, he measured it. Lorentz measured it, and what is the Lorentz equation? F is equal to Q into V cross B. F is equal to Q into V cross B. You must have heard this. You must have heard this equation before. How you must have heard it in a different way. F is equal to QVB. F is equal to QVB. So that is correct only. We need that equation. We have to learn that equation. But this is the exact formula of that equation. F is equal to Q into V cross B. So what is Q? Q is the charge. What is B? The velocity. And what is B? The existing magnetic field. Suppose this is the magnetic field, like for example, so this is the magnetic field we have. So this is, what is B? Okay. So what is the equation? What is V cross B? F is equal to, that magnitude of F is equal to Q into V into, so I can say that this is the magnitude of V into magnitude of B into sine theta. Okay, that is V cross B. So I can also write it as F is equal to, that is the vector notation only, Q into modulus of V into modulus of B into sine theta. This is not magnitude. So I mean this is not the magnitude. This is a vector representation. So we need a vector. Okay, n. And what would be the probable direction of that? What would be the direction of this force? So that we will discuss. The magnitude we have got, the direction we will discuss. You do not worry about that. Okay. So next is force acting on a charge when it moves in a magnetic field. That is what is the same thing, that F is equal to QVB sine theta or Q into V cross B. But another problem is there. Suppose there is an electric field also there. Suppose there is an external electric field there, then what will be the value? Because we all know that if a charge is there, look at this, if this is an electric field, a charge is placed here, so then there will be an interaction between it. Like it need not move, it doesn't want to move around to act of force due to the electric field. Why? Because if a charge itself is placed here, then it will produce an electric field. Already electric field is there. So if you place a charge over there, then there will be an electric field, there will be an extra electric field over there. So that is why there will be a force which is equal to F is equal to QE. F is equal to Q into E. So what will be the total force acting on that if there is an external electric field also? So that is equal to, I'll write it here, F is equal to, look at this, F is equal to QE plus Q into V cross B. So you can take Q outside, so F is equal to Q outside E plus V cross B. So this is the total force. This is the total force. This is the total Lorentz force. So if there is a magnetic field and electric field, then the total force will be F is equal to Q into E plus V cross B. Okay. So next is, next we will discuss the direction. In which direction it will move. So look at this. This equation only we need this equation. Okay. First one, the properties I am going to discuss. This force is directly proportional to what? The charge, the amount of charge or the quantity of charge of that particular particle. Alright. So this is directly proportional to Q. So I would like to write it somewhere here. Okay, this we will write again. No problems. Okay. So listen, all of you listen. So first property, this force is directly proportional to the charge Q. Second one, this force is directly proportional to the magnitude of velocity, in which velocity it is moving, and also this is directly proportional to the magnitude of external velocity, and it is also proportional to what is theta actually. It is proportional to theta. What is theta? Theta is the angle between velocity vector and magnetic field vector. So theta is angle between V vector and B vector. Okay, it is also proportional to theta. And again, look at this. And the direction. Next we are going to discuss the direction. In which direction the force will act? It will be perpendicular to both V and B. So we know the cross product rule, the screw rule, right? So if B and V are both are perpendicular to each other, and both are in some direct angles theta, and Fm will be, and force will be perpendicular to both what? V and B, both velocity and magnetic field. Please keep in your mind that. Okay, just exactly as cross product. How would be the direction in cross product? That is the same direction. Okay, if for example, so this is B, this is V, so V cross B. So in which direction? That direction. If this is V, then in this direction. You got it? So this is what is the direction of this force. Next is one more thing I would like to tell you. And let me ask you one question. What about the electric Lorentz force? What is the direction of electric Lorentz force? Is it perpendicular to something or Q or something else? Absolutely not. It is in the direction of electric field. Electric field is from positive to negative. So if there is a positive charge, it will move in this direction. So the force will be in that direction, in the direction of electric field. That we have learned in electrostatics. I have given a recall only. Okay, so this is what is the whole idea. Okay, about Lorentz force and the direction and everything. I think you have got it. So now we have to discuss the application of some of the applications, and one of the famous devices, that is cyclotron, and the cyclotron frequency and how does it work, etc., etc. All the things we have to discuss. So let's discuss about that. And if you want to make a note on this, like take a note and take a pause the video and take a note, and then we will move on. Okay. Okay, I think you have got a chance to write down, and I'm going to move on. So let's discuss very, very important problems. Very important things in this particular chapter.